In this video, we are going to learn about thermodynamic temperature scale, and we are going to prove about Q1 upon Q2 is equals to T1 upon T2 for the heat engine between reservoir. So first, what is temperature scale? So a thermodynamic temperature scale is a temperature scale that is independent of the property of a substance that are used to measure the temperature is called thermodynamic temperature scale. So now we have to prove Q1 upon Q2 is equals to T1 upon T2. So let's start our discussion. Now suppose this is high temperature reservoir and this is low temperature, and in that two cyclic heat engine is there, 1 and 2. Now since these are the Carnot cycle, so by the Carnot principle we are knowing that the efficiency of these two engines will be same. So we can say that efficiency of this two Carnot cycle is independent of the fluid that is working inside this heat engine and this heat engine, and this efficiency would be independent of the cycle, that how this cycle is performed to carry out all the function. So it is independent of the working fluid, it is independent of the property of this heat engine, it is independent about the cycle. So we can say that efficiency, if efficiency is independent of all these things of the heat engine, so efficiency would be so thermal efficiency would be some function of this temperature Th and this temperature Tl. So we can write efficiency of reversible cycle is equals to some function of we can say Th and Tl. If we say this is small f, now we know n reversible efficiency of reversible cycle is equals to 1 minus Q1 1 minus we can say QH upon QL. So QH upon QL is equals to some function of TH upon TL. This and this is different function because this is small f and this is capital F. So QH upon QL would be some function of TH upon TL. Now we have arrived to this situation. Now let us suppose that there is 3 heat engines as it is shown. 1, this is one heat engine, this is second heat engine, and this is third heat engine, and this reservoir temperature is T1, this reservoir temperature is T2, this reservoir temperature is T3, and it is accepting Q1 and rejecting Q2. Work is W1, and this is Q3, Q4 and W2, and this is Q1 and Q3 and W3. Now we have 3 heat engines as shown, and so if we write this Q1 upon Q2 is equals to function of T1 upon T2. By this we can write for the first heat engine, this is first, this is second, and this is third. Also we can write for second heat engine is equals to we can write for the second heat engine as sorry, if here will be Q2 and here will be Q3, because whatever the heat is rejected by the heat engine first is accepted by the heat engine second, we are assuming for driving this equation, and whatever the heat is rejected by this heat engine second, this heat engine 3 will be rejecting the same part, because if we combine the heat engine 1 and heat engine 2, we will be getting the heat engine 3. So whatever the heat engine 1 is accepting heat from the first reservoir, that much heat is accepting by the heat engine 3, and whatever the heat engine is rejected by the second reservoir, that much of heat is rejected by the heat engine third. So because if we combine the first and second heat engine, we will be getting the heat engine 3. So the accepting part of the heat of the 1 and 3 and rejecting part of the heat of 2 and 3 would be same. And we have supposed that whatever the heat is rejected by the 1 is accepted by the heat accepted by the heat engine 2. Now we will we have derived this for heat engine 1 for 1. Now for 2, similarly we can write Q2 upon Q3 is equals to F T2 upon T3, and for 3 also we can write for 3 Q1 upon Q3 is equals to F T1 comma T3. This is our equation first, this is our equation second, this is our equation third. Now we can see that this F T1 T2 can be related, we can write this Q1 upon Q3 is equals to Q1 upon Q2 multiplied by Q2 upon Q3. Now Q1 upon Q3 is F T1 upon T1 T3 is equals to F T1 T2 multiplied by F T2 T3. This is equation 4. If we say this is equation 4, now we are using this equation for further proof. Now we have arrived to this situation. Now we are seeing that the left hand side is a function of T1 and T3, and the right side has function of T1 T2 and T2 T3. So we have to somehow eliminate this function of temperature T2, and this can be done while assuming that F1 F T1 T2 is equals to some function of phi T1 upon phi T2, and F T2 T3 is equals to some function of phi T2 upon phi T3, and F T1 T3 some function of phi T1 upon phi T3. If we are assuming the function in such a way, so the function of T2 will get cancelled. So we can say here F of T1 comma T3 is equals to phi of T1 upon phi of T2 into phi of T2 upon phi of T3. In this way the T1 and T2 get cancelled, and we are getting phi of T1 and phi of T3. So in the left hand side and in the right hand side we are getting the same quantity, that is T1 and T3 and T1 and T3. So this might be the function that we are requiring. Now Now we know that f T1 comma T3 is equals to Q1 upon Q3, because we have proved by the efficiency formula. Now this Q1 upon Q3, this is equals to phi of T1 upon T3. We have came to this Q1 upon Q3 is equals to phi of T1 upon T3. Now the ratio of the heat taken and rejected by the heat engine is came to be ratio of some function of temperature of the reservoir and of the two reservoirs between which the heat engine is working. Now Kelvin was the first person who said that this function can be taken as the Kelvin temperature, that is T1 first, Kelvin temperature of the thermal reservoir first, and Kelvin temperature of the thermal reservoir third. He said that it will be not wrong to take this function as a Kelvin temperature as the ratio of the Kelvin temperature. So so he was the first who said that Q1 upon Q3 can be written as T1 upon T3, and since then we are assuming this Q1 upon Q3 is equals to T1 upon T3. Now one more interesting facts occur from here, that we know that n reversible is equals to 1 upon Q1 upon Q3. Now this implies n reversible is equals to, since Q1 upon Q3 is equals to P1 upon T3, 1 upon T1 upon T3. Now since efficiency of the heat engine cannot be greater than 1, so the least possible temperature of the substance can be 0. T1 can be 0. Now this T10 can be called as absolute temperature scale. Since we are proving from here that if the efficiency cannot be greater than if this efficiency cannot be greater than 1, so this temperature cannot be less than 0. So this T1 is equals to 0 is called absolute temperature scale. So this not this particular point, but the whole scale comprising of this temperature points are called absolute temperature scale. So our purpose is to derive this formula, that is Q1 upon Q3 is equals to T1 upon T3, which we'll be using in further efficiency question. So this is important that we have to remember. So we have derived the thermodynamic temperature scale, and this can be used. Thank you.